We know the theory behind top-down parsing. You start with a starting symbol, apply production rules, and eventually generate your target input. But a theoretical concept is not a computer program. A compiler requires executable logic. The simplest way to build that logic is to use a recursive descent parser. This is an architecture that directly maps abstract grammar rules into functional software. To illustrate descent, the parser starts at the root node S and branches downward toward the leaves. The recursive half comes from grammar rules. If rule E contains E inside itself, the code mirrors this behavior by simply calling itself repeatedly. Translating the pure mathematics of a formal grammar into these self-referential functions is how compiler students learn to turn abstract syntax into working code. The entire architecture relies on one strict design rule. Every single non-terminal in your grammar must be assigned its own dedicated procedure. This split-screen diagram shows exactly how that translation works. On the left, we have a rule where S produces AA and A produces B. On the right, we write a distinct function for S and a distinct function for A. Notice the match command. To verify an input string like AB, the parser uses this matching mechanism. The function expects the character A, checks the input, successfully verifies it, and advances its pointer to the next character. But if we feed it the input string AC, the system hits a wall. Function A expects the character B, but the pointer hits the letter C. That mismatch immediately triggers a syntax error. The parsing engine requires no magic. It is simply a synchronized cycle. Verify the terminal characters and execute the function calls for the non-terminals. This workspace diagram lets us trace a complete, successful parsing operation step by step. We have our grammar, an input string of AB, and room to map the software's behavior. The parser fires up its start function, S. S immediately expects an A. It matches that terminal against our input string, consumes it, and moves the pointer forward. Next, S calls the function for A. A expects the character B. It runs its match, consuming the final piece of our input string. The code accepts the syntax. If we overlay a theoretical parse tree for this grammar onto our function call history, the shapes align exactly. The sequence of function calls is more than just a sequence of commands. It is a direct reconstruction of the grammar's hierarchy in code. This mapping breaks down when the parser encounters branching grammars, rules where multiple valid paths begin with the exact same character. This diagram shows the problem. Facing an input of AC, the parser must guess. It blind tests the first branch, successfully matching A, but fails at B. To recover, it retracts the path, resets the pointer, and attempts the alternative. This algorithmic penalty is called backtracking. In a tiny script, backtracking is harmless, but in a massive modern programming language, this constant cycle of guessing, failing, and resetting creates massive computational bottlenecks. Backtracking slows a parser down, but another architectural trap will break it entirely: left recursion. Look at this left recursive rule. E produces E plus T. When converted to code, function E's first instruction is to call function E, which calls E. Without ever checking the input, it stacks downward infinitely until the system crashes. To survive top-down parsing, a grammar requires rigorous pre-processing. Engineers must eliminate ambiguity, factor out common left prefixes, and completely strip away left recursion before writing a single line of parser code. Recursive descent is an effective starting point because it offers a direct, readable translation of grammar rules into code. However, its heavy reliance on blind guessing makes it entirely too slow and fragile to scale into modern production environments. To build faster compilers, developers needed a way to eliminate backtracking forever. They needed parsers that could intelligently look ahead at the input and choose the correct path instantly. An evolution that requires predictive parsing, first and follow sets, and the logic of LL1 tables.